Welcome back and Happy New Year. We're going to take a look at the first of several theorems, several important theorems in symplectic geometry in this course. And I'm going to argue to you today the first of these, which is the Darboux-Weinstein theorem. So I've referred to this theorem a couple of times throughout the course. And that's the one that tells us that any symplectic manifold, so you have some symplectic manifold M, some even dimensional manifold, and you look at some point in that symplectic manifold, then there exists a little neighborhood U around that point where this chart is diffeomorphic to the symplectic manifold R to the 2n with the standard symplectic form. Omega is the sum of dxj, dyj, wedge dyj. So that's a result that I quoted to you before informally, and it's a very important result because it tells us that there's no local invariance in symplectic geometry. Everything in symplectic geometry looks locally just like this canonical example. Now that's an important statement that we should clarify and understand, sort of understand in what setting this is to be expected to be true and under what conditions. And so we'll formalize that today as a theorem. And I'll give you something looking like a proof, which is to say it is a summary of a proof. So obviously this theorem is a theorem. There is a proof out there. There are technical details, and there is in fact one big step that I'll just assert in the argument of this theorem. But what I'm going to give you today is as near as possible a complete rendition of the proof of this theorem. Now we're not just going to prove this result here. We're going to prove something a little bit more general, which is this. Not just how symplectic manifolds look around points, but around submanifolds. So the theorem we're going to prove today is going to include this as a corollary, this statement here. And it goes as follows. So let Y be a submanifold of X, some symplectic manifold. And suppose we have two closed two forms on Y. On X, sorry. And the thing that's interesting about these two closed two forms is that they're the same on this submanifold Y. So they could do something completely different outside of the submanifold Y, but on Y they're exactly the same closed non-singular two forms. So the picture is you have your big manifold X, this is X, and then you have some closed some submanifold Y, which is some lower dimensional manifold stuck inside X. You have two closed two forms, two non-singular closed two forms, which agree on this submanifold Y, but possibly not on X. Then there's a neighborhood of Y inside X and a diffeomorphism smooth map with smooth inverse going from U to X such that if you apply f to the submanifold y, you get the submanifold y, so it leaves y invariant. And if you pull back the one form omega 1, you get if you pull back the two form omega 1, you get the two form omega naught. So let's make a comment now about this theorem and why it has anything to do with this result that I discussed at the beginning of this lecture. So it's not immediately obvious that this theorem, if true or not, has anything to do with that. So we have to argue, make some kind of argument that that's at least more general. And well, the place to get started is to select for y just a point. If we take for y a point P, so the submanifold is just this one point space, then the theorem says, if you apply it to this example, just taking what we've written in that theorem and applying it to the case where y is a point, then we're led to conclude that if we have two non-singular closed two forms, omega naught and omega 1, that agree on the tangent space of a point, then we can find a neighborhood u of y and a diffeomorphism which distorts omega 1 into omega naught. Now, the reason this implies the result that we want is that at a point on tangent space, we can find a map that makes omega 1 the same as omega naught because they're vector spaces. And we know the linear transformation which block diagonalizes our closed two forms in a vector space. For finite dimensional vector spaces, all non-degenerate two forms are equivalent. Up to a linear transformation. And the way this result will work, to apply it to a neighborhood U of the point P, if you like, is we can use the exponential map to extend this linear transformation to a little patch around the point P. Sort of an intuitive way to understand this. So we're not actually going to directly follow this strategy in proving the Darboux-Weinstein theorem, but it's worth commenting that here's how you could convince yourself that it's at least true at the level of a point. Just extend this linear transformation by the exponential map, for example, in the coordinate functions, and then that should give you a diffeomorphism f such that f of p is p and f of star omega 1 is omega naught. All right, so that's how this Darboux-Weinstein theorem can be seen as a generalization of the result that I quoted earlier in the course about symplectic manifolds looking locally just like this model space R2n. Let's actually get into the argument behind this theorem, this more general result. Now, it's not the purpose in this course to dwell on proofs, rather to give arguments and leave you to look up the details. But this proof exploits a trick which is a central theme in symplectic geometry, so it's really worth taking some time to dwell on the ideas behind the proof. So the proof exploits something called the Moser trick, and it's that idea that I want to illustrate in going through the argument for this theorem. So this is not going to be a proof, it's an argument as always, but it's a pretty complete argument. So first I'll give you the intuitive overview of the argument, then we'll get into some of the details of how to implement these ideas. So the Moser trick. Well, we've got this manifold X, some submanifold Y. We have two non-singular closed two forms on Y, on X. We've got omega naught, and when you restrict it to Y, it's equal to omega 1. And what we want to do in this argument is find a map F, although I think, no, I guess in the proof I end up using the letter F. A letter F which pulls this form back to this form, not only on Y, where it's kind of trivial, right, because they already agree on Y, but in some neighborhood around Y. I'm going to draw it like this for a reason. And the idea of the Moser trick is to find this map by interpolating between these two non-singular closed two forms. So in the Moser trick, we build a non-singular closed two form omega t, which when t is 0 is omega naught, and when t is 1, it is omega 1. So this is a one parameter family now of non-singular closed two forms. And the idea is to find a diffeomorphism which pulls back omega t to omega naught. And one way you could do that is just write out that f of t on omega t I think it's omega naught, yeah. And if you look at this equation here, that's a pullback of a diffeomorphism applied to an omega t, and we want that it's always equal to omega naught. But that doesn't change, right? Omega naught is constant. So this statement's certainly true when t is naught. I've got it the wrong way around, haven't I? Hang on. I'll try and be consistent with what I write later. So 1 minus t omega naught. Yeah, that was what I wanted. So we'll just do it this way. It doesn't matter which way we do it. So when t is naught, when t is 1, sorry, we want this to be true. Something doesn't look right. Yeah.
Should it be ft omega t omega is equal to omega 0? So
Yes. Yes, it should be.
And f1 is
F1 omega 1. Yeah, okay. I'm confusing myself this morning. All right. That's what it should be, yes. Now, if you look at this thing here, right, so the left-hand side depends on t, but the right-hand side does not. That's what I wanted. So if you differentiate the left-hand side and the right-hand side, you get 0 here and an equation here. But omega t, well, we know what that is because we just chose it to be this. So the idea is now to find a diffeomorphism which locally obeys in t an equation which annihilates this thing here. And that's the idea of the Moser trick. And then you have to extend all this to a neighborhood around y. All right, let's get into it. there's an equation that we have to find. We have to find a vector field that generates this diffeomorphism f of t. F of t is just a one-parameter family of diffeomorphisms. So we have to find a vector field which generates it. Otherwise, well, we've already lost. So let's just recall some comments about one-parameter families of diffeomorphisms. Okay, let's just remember what is a one-parameter family of diffeomorphisms. Well, it's a map from W cross I into Z, which is smooth, yeah?
Is the subscript of phi a star or a t?
Oh, what is the subscript of phi? That's a T, sorry. I don't know why I drew a star. There we go, it's T. We have a one-parameter family of maps, and we've looked at these several times before in this course. We can differentiate this one-parameter family of maps with respect to t, and that'll give us a vector field. And so we're going to give that vector field a name. So you start with some point p in your manifold, you flow it under phi of t, then take the derivative with respect to t, that'll give you a vector at that point, and that vector is called psi of t. And that gives us a way to select a tangent vector at every point in the manifold W. Now, that doesn't give us a tangent vector field, it doesn't give us a vector field on Tz, because W is only a family of maps of W into Z. So there might be some stuff where you can't define this vector field, but that won't matter. At T. So given such a one-parameter family of diffeomorphisms, or indeed just smooth maps, we can make various constructions with k+1 forms and interior products and internal products and so on. We can pull back, for example, the result of putting in the tangent vector xi t in some k+1 form, and then we can pull that back. That's something we can do. And what is it? Well, that's a k form on W. So even though this is not a proper vector field necessarily on Z, this certainly is a k form on W. This will turn out to be very important, this equation here, because this is exactly the construction we're going to use to build our diffeomorphism phi t, f of t, sorry, in the actual argument. And to complete that argument, we're going to let psi of sigma of t we're going to build a smooth family of forms on our manifold W. The purpose of these sigma t's will be to allow us to place omega t in this equation later on. So suppose we have this family of a smooth family of k+1 forms on Z, then I'll just remind you of the local equation that this thing satisfies in T. So, well, first comment is that the pullback of this family is indeed a smooth family. Okay. And then also this family here think of this as sigma t, obeys a local equation of motion in T. So we've derived this equation before, so the pullback of a diffeomorphism is the Lie derivative. When you differentiate the pullback, you get the Lie derivative coming down, and we use the Leibniz rule to push this derivative through both of these. Sorry, the chain rule to push this derivative through. And so if you do that, then you come up with the following equation. Obeyed by this pair here. Now this should sort of look familiar from the original intuitive overview I gave of the argument. And the beauty of this expression is that it's local in T. And we can simplify it a little bit because we know that a nice form for the Lie derivative involving the exterior derivative and this interior product. So we're going to rewrite this right-hand side here a little bit. have that d dt phi t star sigma t equals, and here we exploit the fact that the Lie derivative is di plus id. And that's about as far as we can get at this stage. Oh, well, we can exploit the fact also, yeah. Whenever you have the pullback of d of something, that's the same as d of the pullback of the something. Useful observation to keep in mind, so that we can exchange d and phi of t here in that line here. So we have our final result now. And our objective in this argument is to make sure that this right-hand side ends up being 0 when we apply it to the special case where sigma t is given by this omega t that I introduced at the beginning of the argument. So let's actually look at this expression a little bit to see if that might be a thing that could happen. Well, we've got d of sigma t. Now sigma t, if sigma t was this omega t, so I'm going to bring that up again. So here's what we're eventually going to apply this formula to. So if you look at omega t here, it's just the sum of two non-singular closed two forms. If you apply d to that, then you get 0. Boom. So that term is will definitely vanish. And then you want to choose d, and then you know what d sigma t dt is in this case here. It's equal to a constant non-singular closed two form. And you want to balance that against this term here. So you want to find a vector field psi of t such that this term exactly equals that term there. So that's where the difficulty lies.
Sorry.
Yep.
Like, shouldn't it vanish in all cases because the sigma t is an interior product with zeta t?
So you're saying because shouldn't this vanish as your argument because
No, because I mean the first term in this.
this term.
An interior product, we have twice the interior product with zeta t. Shouldn't it vanish in all?
So the question is, this is the interior product with psi t in sigma t, shouldn't this vanish? Well, only if that's a symplectic vector field. So we don't know any, it's not even a vector field, this is the main difficulty.
That was an example. Yeah, can you just
Yeah. All right. Yeah, so the main difficulty is getting some map that works outside of y. So let's go back to our picture. Here's x, and here's y. So everything's fine on y. We don't need to do any work whatsoever. Now what I want you to do is remember this remark that I made after stating that the theorem in the case where y is a point. So when y is a point, the way we can get a diffeomorphism that works at all is we have this exponential map around that point, and that exponential map is the diffeomorphism. We'll start our diffeomorphism off in this one parameter family of diffeomorphisms. So we need to have a diffeomorphism to begin with, right? And we don't have one to begin with. So one of the core difficulties in this theorem, on the argument in the proof of this theorem, is finding a diffeomorphism defined not just on y, but on some neighborhood around y. And I'm just plain not going to prove that part of the theorem. So this is, I'll call this problem 1. We want a diffeomorphism phi naught of x into y, sorry, of x onto y, such that if you apply it so getting a diffeomorphism at all defined outside of y is non-trivial. And if you furthermore want that diffeomorphism, the last thing you want is that the diffeomorphism sort of maps y to some other place. I mean, you don't want to mess up stuff that's true on y. So you want to find a diffeomorphism phi of t x onto y such that it's the identity when t is 1 and it always is equal to phi t of y for all t. Now, such a thing has a name. This is called a retract. So a smooth retract is the name of this thing. So this problem 1 is equivalent to finding a smooth retract of x onto y. So that's the first difficulty we have to overcome, finding some way, finding some map that extends outside of y. Now this I won't at all address in this argument. I'm not going to prove that that's possible. It comes under the rubric of the tubular neighborhood theorem. So the existence of these retracts is a generalization of this idea of the exponential map. So I'll draw a picture and I'll explain why I don't want to get into this proving this result in this course. So the picture itself, I think, explains the proof. So let X just be some flat manifold. Let it just be Euclidean space. And let Y, here's Y, is our submanifold in X. Now, how might you design a map that smoothly retracts on to Y in some neighborhood of Y? Well, just looking at the picture here, one way you might go about it is you find the normal vector to this curve everywhere, and you draw a picture like this, right? Now, because y is smooth, there's no kinks in here, then if you add together all these little submanifolds that are tangent to the normal vector of y, then you should carve out a piece of x. And that piece that you carve out should, as long as the length of these pieces aren't too long, be a nice open subset of x. And this is the tubular neighborhood here. And the reason for the name tubular neighborhood isn't really apparent from this picture. In 2 dimensions, you don't really see why we would call it tubular. But think about 3 dimensions, right? So if you have a 3-dimensional ambient manifold like the space we live in, and you have a 1-dimensional submanifold running through this space, and you find all the normal vectors to that 1-dimensional space, and you flow out as far as you can, then you'll form a tube around this 1-dimensional manifold. And that's the neighborhood U that we need. And how do you get this smooth retract? Well, you just do the exponential map. So you got some point there. How do you get to that point? Well, you just do the exponential map along this normal vector. And so that defines for you, as long as the length of these things is short enough, this defines for you a diffeomorphism that you can use to retract every point onto this line here. Now, the reason I don't want to get into this is to do this properly, we really should use the language of fiber bundles, and I don't want to do that in this course. I don't see really the need to go into all that additional formalism. But there, in the language of fiber bundles, this is the 0 section. Y is the 0 section of the normal bundle that you create around the submanifold Y. And then you argue that the 0 section is you can retract onto the 0 section via the exponential map on that bundle. So that's how you cope with problem 1. So we're just going to assume that we've coped with that. So we're going to assume it into the result. So we're going to prove a weaker result in this course. Now we're going to exploit this formula over here. Call it 1. We have ourselves some diffeomorphisms to play with now. So we're going to exploit 1. We're going to integrate it to write out a formula relating some form on X and its pullback under this diffeomorphism phi naught of phi t at time t is naught. So it's one of the most satisfying proof techniques available in analysis. We're going to differentiate and integrate. The fundamental theorem of calculus. Now, the third term vanishes, of course, because sigma is just constant. And this I symbol, what does I mean? Well, I applied to some form is just integrate from 0 to 1 phi t star of I of psi t alpha dt. So that means that I is a map from k forms, or if you like k plus 1 forms, down to k forms. Well, k so you give it a k form, it drops its order by 1 with this interior product, and then pulls it back to another k minus 1 form. Alright, now's where we introduce our omega. So as before, we set omega t to interpolate nicely between the two non-singular closed 2 forms that we have, and you can write this as omega naught plus t sigma, where sigma is just the difference of the two, like so. So sigma is a constant 2 form. And now, what do we know about sigma? Well, on y, it's pretty simple. It's 0, because these two forms are the same. And we also know, thanks to our nice smooth retract, doesn't change that fact because it behaves as the identity on y when t is naught. And we also know that d of sigma is 0. Actually, that's not so deep. I mean, phi naught of star of 0 is 0. Oh, did I? The question is, why is there a sign change up there? I don't believe there is a sign change. I think I just miswrote that. In any event, it's 0, the second term, when we want to use it. I mean, what did I write here? It's definitely got to be a plus, right? Nothing has changed. So I just miswrote this in my notes. There. So star is a very important equation, especially when we exploit this data here. So d sigma, what's d sigma? It's 0 when we apply it to the sigma coming from this omega t. So star, and we know that phi naught star of sigma is 0. So we've actually learned that this form sigma is not only closed but exact. So there is some alpha that when you hit it with d gives you sigma. It's pretty neat. Otherwise, this is Poincaré's lemma in disguise. And we even know what the alpha is. It's just this I applied to sigma. And also, well, note that if you restrict alpha to y, you also get 0. So now we know that omega t restricted to y is equal to omega naught restricted to y, which is equal to omega 1 restricted to y. So on y, omega t is constant. And that has the important consequence that omega t restricted to y is non-degenerate. And that has the further important consequence that there's a neighborhood of y where omega t is non-degenerate as well. And I'll just make a comment on why that's a consequence. The equation of degeneracy is a polynomial equation. So it just means that the determinant is 0, ultimately speaking, of the matrix representing omega t. And that is an equation which has a lower dimensional subset as a solution inside of X. And that can't possibly be infinitesimally close to Y. So there's at least some region around Y where that equation isn't fulfilled. All right, so this thing is non-degenerate, especially in a neighborhood U of Y. So we can use it to get a vector field, and we got all the information we need to get ourselves a vector field. So we have a 1 form, alpha. We have a closed non-singular 2 form, omega t. And whenever you have a 1 form and a closed non-singular 2 form, then you can define implicitly a vector field eta t via that equation there. And this vector field will define a diffeomorphism, and that diffeomorphism will be the one that we want. So we have ourselves a nice vector field on U around Y. Let's call it A to T. We integrate this to get f of t, and these f of t's are the ones that we want. Now, the first thing we note is that f of t restricted to y is the identity, does nothing. And that is a consequence of, where did I write it? Up there, yeah. Alpha y is 0. So that's a good start, at least for diffeomorphisms that fix y. Now, it might be when you integrate out this vector field that f of t doesn't exist for all the t that you want it to. You know, the fixed point theorem, which is lurking underneath this argument here, gives you a neighborhood, but not necessarily one that will work for all t that you want. But if you restrict to a smaller neighborhood around y, then you can get f of t to exist for longer. And indeed, we want it to exist for all t between 0 and 1. So summarizing what we know that f of naught is the identity, and d omega t dt is sigma, and then when we put this together with our final equation, we will get the thing that we want. Okay, now let's apply again the trick of differentiating and integrating. Let's now look at what happens if we apply f1 star to omega 1. How can we get that expression? Well, we know how to get that expression. We integrate the derivative. So we do it twice in the course of this proof. Once to get the vector field a to t, and once again to get f. Okay, that's fundamental theorem of calculus. And then in the next step, we'll exploit what I believe I called 1. Okay, let's spend a moment looking at this. So when we differentiate the pullback of a k-form, we get the Lie derivative plus the change of the k-form. So let's look at the change of omega t. What is that equal to? Well, we wrote it down over here. It's just sigma, this constant 2 form there. So that's the first term coming from our identity I that we derived at the beginning of the argument. And then we have 2 terms here, the Lie derivative coming down from differentiating this pullback, which we then replace with di plus id. Well, the id term vanishes because d of omega t is 0, so we're just left with this term here. But look at this, right? When we apply I eta t to omega t, we get minus alpha in here. But alpha is exact. So d of d is 0.
D alpha is sigma, right?
D alpha is sigma, goodness me. Sorry, d alpha is, it's minus sigma, now it all works. And so we get minus sigma, and that is 0. So that's the end of the argument. We start with the diffeomorphism which retracts the manifold X onto Y. We use it to get a vector field psi of t. We then use omega of t to build another vector field eta of t, which we integrate to get the diffeomorphism f of t. And that concludes the argument of the theorem. The missing major step, if you like, is this tubular neighborhood theorem, which, if you're familiar with fiber bundles, you should have no difficulty in understanding as soon as you understand the exponential map and and how to define a fiber bundle and a normal bundle. As I said, we're not doing that in the course, and I'll just relegate that part of the argument to the picture that I drew. Otherwise, we are done, I think, for today. I won't start the next topic just yet. In the next lecture, we'll look at the statement of the Dijkstermat-Heckman theorem in the case where we have a circle action on the symplectic manifold, and we'll go through some examples of this theorem and argue via example that it's likely to be true. And then in the following lecture I will sketch somehow the argument of that theorem and tell you about its generalization. And then in the final lectures we will apply some of the knowledge that we've gained to quantum mechanics. So we'll see how quantum mechanics gives us a symplectic manifold, and the Schrödinger equation gives us a symplectic flow on this manifold. So it's a very unusual perspective if you think about classical mechanics and quantum mechanics being different things, but it turns out that indeed quantum mechanics is also symplectic. That's the topics for the remainder of this course, but for today, I think I'll stop here, and thank you very much.